I'll get started. So, remind you, last time we introduced a radian measure for angles, right? And we started our work on sine and cosine, right? So, I'll just remind you, we have unit circle, right? And if you pick a point on the unit circle, right, then the that was just the projector, right? It beeps when it goes off. It's a very strange feature. I don't know many other things that just randomly beep when they turn off, you know? Anyway, so the standard angle, theta, measured counterclockwise from the positive x-axis, right? This point right here has coordinates what? Cosine theta, sine theta, right? And let's see here. Last time, we figured out what? We figured out that the cosine of pi over 4 is equal to the sine of pi over 4 is equal to 1 over root 2. I would point out that that's also equal to the square root of 2 over 2, right? So sometimes you see it written like that. And of course, this is also equal to cosine of 45 degrees and also sine of 45 degrees. So I try to talk about degrees and radians in here, right? Okay, so what are the special angles that we're all supposed to know, like sine and cosine of the special angles by heart, right? Without a calculator. So the special angles are, of course, like 0, pi over 2, right? We also figured out sine and cosine of pi over 2 and 0, right? Cosine of 0 is 1, sine of 0 is 0, sine of pi over 2 is 1, cosine of pi over 2 is 0. We mentioned those last time. But the other special angles are like 30 and 60 degrees, or pi over 6 and pi over 3, right? So I think it's a good exercise for us to work out cosine of 30 degrees and sine of 30 degrees. How do you do that? So here's how. So we have our unit circle, right? And what we're going to do is look at an equilateral triangle, right? So there's an equilateral triangle you can fit here like so, right? Now this is the unit circle. So the length of each leg of the triangle is what? It's 1, right? So this is 1, this is 1, and this one's also 1, right? So if the whole length is 1, what's the length from like here to here? 0.5, yeah, 1/2. Right? Now it's an equilateral triangle. What's the sum of the angles in any triangle? 180, right? 180 degrees or pi radians, right? Now in equilateral triangle, the angle at each vertex is equal, right? So 180 divided by 3 gives us 60 degrees. So we know that this is 60 degrees up here. We know that this angle down here is 60 degrees. And also from the symmetry of the problem, you can see that the middle angle of 60 degrees is bisected by the x-axis, right? So you got 30 degrees above and below. Certainly, I hope you can agree, this right here, 30 degrees, right? Can you see that? Everybody see it? Now, if that's the case, what does that make this point right here? That makes this point right here cosine of 30 degrees, sine of 30 degrees. Now, we already know that the y component is what? we'll have to fill in that blank. But the y component is a half. You guys just told me that a second ago, right? So we can already see from this picture that the sine of 30 degrees is 1/2, or we're trying to figure out what is the sine of 30 degrees and the cosine of 30 degrees. Now you're like, well, I got a calculator, so I could plug those in. That's true, but just give me here a couple minutes to show you how we can derive these things from analytic geometry. We'll soon enough be using calculators. Perhaps this is after the robot holocaust. We can't trust the calculators. They're all evil, you know, after they turn on Skynet or whatever. So you guys tell me, if that's half, what has to go here? Remember, we know that x squared plus y squared equals to 1 for the unit circle. So we're trying to figure out what x is. So we have x squared plus 1/2 squared equals to 1, which gives me x squared equals to 3/4. I take the square root of both sides. Remember, I have to allow for plus or minus. So algebraically, I get x is equal to plus or minus the square root of 3/4, which simplifies to plus or minus the square root of 3/2. But where am I? I'm in quadrant 1, right? So what do I put there? Plus or minus, I have to choose plus, right? So there we go. The square root of 3/2 is the missing contestant here. And so we get the cosine of 30 degrees is the square root of 3/2. So these things are actually not that hard to derive, right? I think a lot of times we just tell students these things in trigonometry without like showing it. I think it's a good exercise for us to show it. And also, moving on here, what about the cosine of 60 degrees? And the sine of 60 degrees, how are we going to do those? How about this time, instead of drawing the equilateral triangle along the x-axis, we draw an equilateral triangle about the y-axis, like this, right? Then if you look at it, see what goes on here? Just by the symmetry of what's happening here, you can easily see that the x and the y components of the point just flip-flop. Like up here, if I draw in my picture better, yeah, this is about 45 degrees. This is so horrible. I can't bear it. I had to fix it. Let's try it again. So 60 is more like up here, right? Probably went too far. But anyway, this point would be 1/2 square root of 3/2, right? Now, what's going on angle-wise is the angle off the y-axis, right? This one right in here is 30 degrees. Man, I guess you can't even see it. I need to stop using this blue chalk. It's ghostly. All right, 30 degrees there, right? So that makes, remember, what do we have? You remember, what do we mean by complementary angles? Do you remember this term from high school geometry? Complementary angles are angles which sum to 90 degrees. So if you have a right angle, the angles which sweep it out are complementary. So here, this 30-degree angle is complementary to this 60-degree angle here, right? And so that's why I know this is equal to cosine of 60 degrees, sine of 60 degrees. So it turns out the sine of 30 degrees is equal to the cosine of 60 degrees. They're both a half. And the cosine of 30 degrees is equal to the sine of 60 degrees. And it's the square root of 3 over 2. So let's see here. We can collect our thoughts over here. All right, so right here we have square root of 3 over 2, 1/2. This one, 1 over the square root of 2, 1 over the square root of 2. And up here, we have 1/2 square root of 3 over 2. And of course, up here, we have 0, 1. Here we have 1, 0. And an arbitrary point on this has the form what? Cosine theta, sine theta. Let's see here. Let's label the angles. What are we looking at here? Yeah, exactly. So this is theta equals to 0. Theta equals to 30 degrees. Theta equals to 45 degrees, right? Theta equals to 60 degrees. Theta, all right, fine, I'll flip the font. Theta equals to 90 degrees, right? All right. Oh, well, I'm having stylistic conundrums. Pi over 6, pi over 4, pi over 3, right? Radians. So let me show you how we can find sine and cosine using the idea of a reference angle, right? So I started talking about reference angles day 1. We do it again here. So let's suppose we're looking at this point over here, say minus 2, oh, fine, or curses. It's not big enough. So this point right here, let's say it is at angle 135 degrees, right? So how can we figure out sine and cosine of that point using the reference angle idea? So what's the reference angle to that point? So let me just explain the instructions here. Find cosine using reference angle idea. Now I heard it would be 45 degrees as the reference angle. I agree with that. So the reference angle is it's the acute angle that gets you to the ray in question swept up from either the plus or the minus x-axis, whichever is closest. Negative axis, in this case, 45 degrees like you said, right? And so if this point, if I'm thinking of this as being the unit circle, and I am, right? If you look at this right triangle here, well, you know that the length of this side is 1 over root 2, right? And the length of that side is 1 over root 2 because the cosine of 45 degrees is 1 over root 2, and the sine of 45 degrees is 1 over root 2, right? So then what is the cosine of 135 degrees? What is the sine of 135 degrees? It's not just 1 over root 2 in both cases, right? We have to think through it. They're points on the unit circle, right? So if they're in quadrant 2, we should have y as positive, we should have x as negative. So what do we got? X is negative, right? So minus 1 over root 2 for this one. And the sine is indeed the same, 1 over root 2. So hopefully, like next Monday, I'll have a handout for you guys that has the unit circle with all of the points for the special angles filled in with specific numbers, right? Like I've already filled in the first quadrant up there, but you can continue this picture. Like the point that we just found in this example is like over here, right? Minus 1 over root 2, 1 over root 2, right? So I don't know, like I use this idea a lot in physics. If I want to figure out the coordinates of a point, if I can figure out an acute angle relative to an axis, I can kind of go from there using my knowledge of like 90-degree acute angle right angle trigonometry. Let me show you another example. What if I'm like down here? I want to figure out what are the coordinates of that point on the unit circle. And this is, let's say, 210 degrees. The reference angle this time will be 30 degrees, right? Totally agree? Right, so let me just blow it up a little bit. If I look at a 30-degree triangle, right? Then I know that the opposite, if the hypotenuse is length 1, I know that the opposite side has length 1/2, and this one has like 3 over 2. With the thing I derived at the start of class today, actually. So I can think in terms of the cosine and the sine of 30 degrees and kind of go from there. So like, let's see here. Cosine of 210 degrees, sine of 210 degrees, what are those equal to? So like in magnitude, it should be the same as the sine and cosine of the reference angle. All right. Let me state that again as a theorem. If theta has reference angle theta prime, then the magnitude of the cosine of theta is equal to the magnitude of the cosine of theta prime, and the magnitude of the sine of theta is equal to the magnitude of the sine of theta prime. In other words, sine of theta is equal to plus or minus sine of theta prime, and cosine of theta is equal to plus or minus cosine of theta prime. We have to put in the plus or minus by considering the quadrants in this way of thinking. So You guys tell me, cosine is what? We got square root of 3 over 2. We got a half. Which one is plus? Which one is minus? You're like, that's a loaded question. They're both negative, right? Yeah? Okay, good. So here's a guide. Cosine theta greater than 0, sine theta greater than 0. That's for quadrant 1, right? Cosine theta negative, sine theta positive. That's for quadrant 2. Down here we've got cosine and sine, both negative. That's for 180 degrees all the way up to 270 degrees, not included, right? And in quadrant 4, we've got cosine positive, sine negative, and that's for 270 to 360. Now, we should also be thinking in radians, right? I haven't done much in radians yet today, but this guide I just wrote, right? If I was to put in radians, what are the guideposts, so to speak? Like, this is 0 radians, right? Up here is pi over 2 radians, right? This guy over here is pi radians. Directly down, 3 pi over 2 radians, right? So quadrant 1 is 0 to pi over 2. Quadrant 2 is pi over 2 to pi. Quadrant 3 is pi to 3 pi over 2. And likewise, quadrant 4 goes from 3 pi over 2 to 0. So likewise, cosine and sine and radians share the same kind of sign patterns, right? Let's look at a different problem. So we could keep playing this game, finding, sine and cosine from reference angles. But I think I've shown you enough that you can work the homework problems like this, yeah? So my next example is a little bit different. Suppose you're given, right? Let's see here, find cosine theta and sine theta for theta as pictured. So how would we figure out cosine theta and sine theta, given that it goes to the point that has coordinates -3, -1? You're like, oh, well, cosine of theta is -3 and sine of theta is -1, right? Well, this is wrong, right? Because remember, sine and cosine are given by the unit circle, right? This is not a unit circle. What's the radius of this circle? I'm telling you it's a circle, by the way. It's a circle. So you could use the Pythagorean theorem, right? If you look at this little sort of reference triangle here, right? That has what? It's got 3 here and 1 here as distances, right? As lengths. So how long is the... yeah, square root of 11 is the length of it. It's what? Oh, square root of 10, yeah. I'm very gullible. I'll believe anything. Let's see here. Square root of 10, yeah. I think I may have accidentally given us an example which is like beyond where we are. Yeah, I'm asking what is sine and cosine there, yeah. Oh, I'm sorry. So I have shown you now a problem we don't have the technology to deal with yet. We don't know how to solve this problem. Not yet, anyway. This is actually like a section. Come on. Maybe 5.4? I don't know. So I think in our current way of thinking, the only way to solve this is to be kind of sneaky. What we have to do is to see a unit circle, like just draw a unit circle, superimpose a unit circle here, and then we could figure out sine and cosine from that. So the unit circle is somewhere in here, right? Right, if that has square root of 10 is about 2.2 something or other. Wait a minute, 3.3 something or other. Not quite to scale, but the unit circle's in there somewhere, right? And wherever this point of intersection is, that tells me what cosine of theta is, right? So how do I figure out what that point is? Yeah, I mean, I could use, what I would do is I would use, do you guys remember similar triangles? Remember similar triangles? They're triangles that are like the same angles, but they're different sizes. So like this, there's a similar, the orange triangle would be similar to a red triangle that I could draw inside it right there. The red triangle is really what we want, what we're after. But one of the theorems about similar triangles is that the ratio of sides of similar triangles are equal. Ratio of matching sides, so like the ratio of the opposite to the hypotenuse. So in this case, we could say like 3 over the square root of 10, right, is equal to, because this is 3, and this is square root of 10, right? And then this right here, of course, is sine theta, and this is cosine theta. Now, technically, I have to put a minus because those are both negative, but since they're both negative, the minuses cancel, so we can actually just say sine theta over cosine theta. Man, sometimes it is really, like this chalkboard just does not take the chalk worth anything. It's so slippery. Sine, I don't know what's going on. This chalkboard's really trash. Sine theta over cosine theta. You're like, well, that doesn't let me figure out, but what else do we know? So we, x squared plus y squared equal to 1, or more to the point here, sine squared theta plus cosine squared theta equals 1, right? So this tells us that sine theta is equal to the 3 over square root of 10 cosine theta, right? But we also know that sine squared theta plus cosine squared theta is equal to 1. So if I plug this into that, then I've got an equation just involving cosine squared, cosine theta, right? So I get 9 over 10 cosine squared theta plus cosine squared theta equals to 1, which gives me 9 tenths plus 1 is 19 tenths, yeah? So 19 tenths cosine squared theta equals to 1, so cosine theta is equal to 10 19ths, square root, plus or minus, but we're going to choose the minus because of where we are. So there's the cosine is minus the square root of 10 over 19. And once you know that, you can go back and figure out what sine is, right? Because you just plug it in to here and you get, I don't know what you get. Maybe square root of 9, 9/19 maybe, I don't know. Oh, this right here, right? Duh. So sine theta is what? 3 over root 10 times square root of 10 over 19 with a minus. Anyway, so it is actually indeed minus the square root of, well, you could write it square root of 9 over 19 if you like. You could have kept the 3 up front, but anyway. The under what? Sorry, I missed you.
You wrote
9, 10. I wrote 9. 9. Yes. So what I was replacing sine squared with this right here. So if I square that, it gives me a 9 over the square root of 10 squared, which is 10. So that's why I have 9 tenths. 9 tenths is this quantity squared, and then that's that cosine squared. So this is that term because I'm making the substitution. So I suppose in principle this is something you could logically extract from the 2 sections we've covered, but it's kind of like on the edge of what is a reasonable question. Let me find an example which is a little bit more on the side of reasonable. How about this? Suppose we've got a point on the unit circle. All right, and that point is minus the square root of 3 over 2, 1/2. Then my question is, what's the angle to that point? What's the standard angle there? I heard a gentleman say that theta is 150. Anyone care to agree or disagree with him and or explain his wild conjecture? +90 plus 6. Now, what does 60 have to do with anything?
60 degrees away from the y-axis, down to 30 degrees.
So, but what is 30 degrees? How do you know this has anything to do with 30 degrees is my question. So, this is the reference angle, right? And you know that if you look at 30 degrees over here, right? We figured out that this point is square root of 3 over 2, 1/2, right? Start a lecture today. So you have an intuition already that this point is associated with that point, because you know that this is 30 degrees up, so it must be that this is 30 degrees up. And if this is 30 degrees up from the 180 mark, that must be at 150. These are all hardwired into your brain already, aren't they? Yeah, that's good. So let's see here. So the thought process, though, for this point, this is given. We can figure out that that corresponds to a reference triangle with 30 degrees, right? So that shows me that that this is a 30-degree angle. And if theta prime is equal to 30 degrees, and theta prime plus theta is equal to 180 degrees, then theta is equal to 180 minus 30 degrees, which is 150 degrees. All right, good. Let's see here. Now, of course, at some point or another, we should start using our calculators, right? So, let's see here. Of course, I have forgotten mine at the moment, but let's see if I can figure it out. So these are technology exercises. I don't think I've actually assigned any of those, but this would be good exercises for you guys to see if you can check the following. Let's see here. Sine of 98 degrees. What's that? The cosine of 98 degrees. What's that? What's the sine of 310 degrees? Let's work that out. Actually, oh no, I was about to say, my question for you actually at the moment is, are any of these things we could figure out just using standard, like our special angles? And I think, well, what's that? I thought so too, but then I thought, wait a minute, 360 minus 310 is what? 50. See, I was fished into the same thing there for a second, but then, so here I don't have my calculator with me, but let me just see if I can conjure it. Oh rats! My sheet of conjuring only goes to 90 degrees. Poor planning on my part. Now it won't seem magical. I got to rely on you guys. Well, let's see here. We could, or I could use this. This is also, I mean, if you guys want to, how about you tell me these and see if we get agreement. Right? Math is done by consensus, right?
For the first one, I got
0.990. Can you give me the fourth?
2, but you can round it up to 3.
0.2?
Yeah, 0, 2, but it's 0, 2.3.
Oh, so it's 0.3, okay. How about cosine of 98 degrees?
Negative
0.139?
Yeah, 1.
1? All right. What about sine of 310 degrees?
It's -0.766.
Negative 0.766. So let me give you some arguments for why those numbers make sense. All right. First of all, 98 degrees is in what quadrant? It's in quadrant 2, right? That's where sine should be positive and cosine should be negative, as we see they are. Right? What else? The 310 degrees is in quadrant 4, right? And so there we're negative, we're below the x-axis, so that the negativity makes sense there. Also, if you want to think about this geometrically in terms of approximation, 310 degrees is, somewhere down here. It's 50 degrees shy, right, of the x-axis, right? That's close to 45 degrees, right? 1 over root 2 is 0.707, right? This is 0.707, roughly speaking. So, yeah, it's a little bit further down than 0.707. That seems like a very reasonable figure. But anyway, let's see here. What are other patterns we should observe about? Well, there's many, many patterns we should observe about sine or cosine, and we will get to them in due time. Let's see here. Any questions about homework? No? All right, then my question to you would be, what do you think about sine and cosine as functions? What can we say about sine and cosine as functions? What would their domain and what would their range be if we think about sine and cosine as functions? By the way, the complete reference angle unit circle is actually on page 468. If you don't want to wait for me, it's right there.
You said sine, cosine got a domain and a range?
Yeah, what would domain and range?
It wouldn't be infinity?
So you say that the domain
Infinity.
of cosine theta and the domain of sine theta is everything? Yeah. Minus infinity to infinity, right? The whole real line. Totally agree, because we have that coterminal angle idea, right? We don't just go 0 to 360. We can keep adding 360 and keep going round and round and round, one way or the other, right? So yeah, the domain is everything. What about the range? Nope. Like the domain, so the range of sine and cosine corresponds to possible coordinate values on the unit circle, right? Like the biggest, you think about it, so that's the unit circle, right? Like what's the top point here? 0, 1, right? Down here, 0, minus 1. Over here, minus 1, 0. Over here, 1, 0. And remember, cosine squared theta plus sine squared theta equals to what?
So would the range be 1 to 1, 1 to 0?
The range would be minus 1 to 1, exactly, yeah. Because this means that neither sine, this equation right here, and among other things, if cosine was 2, that would violate this equation for sure, right? You can't have sine or cosine be larger than 1 in magnitude. So that's it, yeah. The range of cosine is the range of sine, and it is minus 1 to 1 included, yeah. So they're kind of boring functions in a sense, but that's that. I think I've said pretty much everything that there is to say in sections 5.1 and 5.2 at this point. So with the time that remains here, which is about 4 minutes, right? Let me just talk a little bit about just plain old right triangle trigonometry. So, so there's different ways to start trigonometry. The one is the way we've gone, which is to follow the book, right? We introduced degrees, we introduced radians, we talked about sine and cosine as a consequence of the, unit circle, right? But the other popular way to introduce trigonometry is in terms of right triangle trigonometry, right? And right triangle trigonometry you probably recognize from high school. You look at a right triangle, right? And you have one of the angles is right. You call the other angle theta, wherever it is, right? And then the relation of the sides to the angle are typically what? Labeled opposite, right? or op, adjacent, or edge, or hypotenuse, like here, right? And a lot of times when we're talking about this sort of thing, you might call this like, well, you could call this x, you could call this y, and or you could call, let me use AB. Then this would be C, right? And of course, you know the relation, right? A squared plus B squared equals to C squared, Pythagorean theorem, right? And then in terms of right triangle trigonometry, you simply introduce sine and cosine as the ratios, the geometric ratios. Sine theta is opposite over hypotenuse, which is B over C, right? And cosine theta is the adjacent over the hypotenuse, which would be A over C, right?
We have used it to solve that problem?
We could, yeah. Yes, yes. If we knew this, then my difficult problem becomes trivial. Because then you could have used that problem we had. You could have looked at this thing here, and you'd be like, well, that's square root of 10. And what was it? I've erased it, haven't I? Oh, is it that one?
Yeah,
3? Yeah. And was it 9? Yeah. So in that, if you knew this, then that problem becomes absolutely trivial. And, you know, you get, okay, so sine theta is, what, 3 over the square root of 10, and cosine theta. Now, but what's the rub? For that problem, we have to remember the context, right? I've lost the context here. So I'm just thinking of this as being, let's say, theta prime, right? So this is really cosine theta prime, and sine theta prime and cosine theta prime. Then we have to use the referencing idea to put back in the minus to get back to my previous example. But that would at least allow us to avoid the whole similar triangle argument that none of us really enjoyed, right? I mean, similar triangles are important for engineering and applications. Like, this is a very, like, important trick for solving a certain class of word problems. But this right here, this whole business is something we'll come back to. There's like a whole section in the book about this later. I just got tricked today because I forget that you don't know that yet, because this is so like built into me at this point. So that will happen from time to time in here. I know too much and I forget where we are. So if I ever do that, you just got to like stop me and bring me back to where we are. Anyway, have a good weekend, you guys. Oh, let me take attendance right quick. Oh, tangent will come next Monday. We'll start into tangent. I think I'll start into section 5.3 Monday probably. Let me hit the camera and I'll